Hello, welcome to another lecture on data formats. Today we have a guest speaker, Michal Med, who is a geodata expert and who worked at the State Administration of Land Surveying and Cadastre. And today...
I'm not working.
Yeah, worked.
Yeah.
And who will give us an introduction to geodata. Michal, the floor is yours.
Okay, good afternoon for everyone. I'm just going to share my screen. Yes. So I hope you all see it.
Yes.
Yeah, fine. So my name is Michal Med, and I used to work at Czech Office for Surveying, Mapping, and Cadastre. I was working there with spatial data quite a lot. And I will share some of my experience from there. Also, I was studying at the Faculty of Civil Engineering at Czech Technical University, especially the civil engineering. It's mostly about constructions and this kind of stuff, but I was studying there geoinformatics, which is like informatics, but on behalf of spatial information and spatial data. And this was what I was working there thereafter. And now I'm working at the Faculty of Electrotechnical Engineering of Czech Technical University, and we are focused more on the linked data and ontologies and this kind of stuff. But I also have some expertise in spatial data there. So at the beginning, let me introduce what the spatial data is. What is the spatial resolution of the data, and what is it good for anyhow? So the first thing is the easiest definition is that spatial data are needed to answer the spatial questions. The spatial questions usually are in the type of how far is it, which way to take. If you are standing at the street and someone asks you how to get to the railway station, this is basically the spatial data question. So by giving the directions, looking for the highest mountain in the area is also special type of question. Which bus stops are reachable from my home or from my office in 5 minutes on foot? Something like this. This is also the spatial question. Who has the largest farm in the whole valley? This is also legit spatial data. Or even what historical monuments are visible from my hotel room? This is also a legit question. So basically, the spatial data are data that are helping us answering this kind of questions. So basically, those data has to have some location, and they describe the objects based on their location and also based on their shape. The shape is also quite important. For example, for the last questions about the historical monuments visible from the hotel room, you need to know the shape of all the buildings, all the solid objects in the way from your hotel window until the historical monuments. And you also need to see what is the elevation in the area and this kind of stuff. So under spatial data, you can imagine quite a lot of information because more or less every object you can imagine has some location and some shape. If you are not talking about ideas, of course. I will tell you some basic terminology we are working in, and we are talking about the science, or about the about science. Let's say about the science which is focused on the spatial information. We are usually talking about geoinformatics, geographic information systems, or the geomatics. And the last mentioned term, geomatics, is defined in the ISO Technical Committee 211, which is quite important for the whole geospatial science. because this is the technical committee working on the spatial norms and spatial standards. So the geomatics is discipline concerned with collection, distribution, storage, analysis, processing, presentation of the geographic data or geographic information. If you look at it, you see that there's quite a lot of stuff which is concerned with the geomatics. So it's not only the processing of the data itself. Uh, Usually it is done in software systems called GIS, Geographic Information System, but also the part of the system is not only work of the data analysis or data processing, but also the way how to store the data, how to distribute them, how to publish them, present them to the general public, and also the collection of the data is part of the process. So basically, if you have, I don't know, some surveyors in the terrain, they are also part of this geomatics mm, problem, yeah? And the information, which is only the part of this whole process, the whole setup or framework, the geographic data, also called geodata, spatial data, geospatial data information, or georeference data. They also have the definition in the ISO TC 211, and the definition is as follows: data and information having an implicit or explicit association with a location relative to the Earth. So basically, you can imagine that any data which you can locate in the scope of Earth shall be managed as geographical data. I can now I can make a step back and try to find out two more examples, and both of them are also geodata, and maybe you will not believe it in the first place. The first thing is that if you have a CD or some other kind of external storage, and you have no labels on that, and stored on that storage, you have an Excel sheet or TXT file or something like that. And in that file, you have stored some numbers. And basically, you don't know what those number means. But in the end, if you get a piece of paper, on that paper, you have something like metadata, where you have described what those numbers means. Let's say that those are the coordinates of all houses in the city of Prague. Then basically it becomes geodata. Yeah, this is one of the examples. And the second example, what also can be handled as geographic data or geodata, but I will show you. This is the map of Mars. To create the map of Mars, processes and programs, data, all that stuff were used as in this similar manner as it would be done on Earth. But the definition of geographical data is the data information having an implicit or explicit association with a location relative to Earth. So this is not Earth, but we can also work with this data as geodata, because this is something which is relatively bound to location, to space. Okay, the next slide. I have maybe one little bit step out, and I will show you one more thing here. Yeah, I was talking about implicit and explicit relation of the data. So you can imagine something there. If we are talking about the implicit geodata, we are talking about coordinates, distances, directions. Basically, this is something which is measurable with some solid units. So for example, if we have coordinates like 14 degrees, 42 minutes and 23 seconds east, and 49 degrees, 52 minutes and 12 seconds north, this is definitely some kind of coordinates, and this is implicit geodata representation. The same is that if I give you an azimuth and the distance, this is also the implicit geo information, because I can locate some other object relatively to my location. And when we are talking about explicit geodata, this is locating the data based on the reference, based on the address, or based on the geographical names. So if someone asks you, where do we meet? You can basically say, let's meet in Wenceslav Square. So this is the explicit geodata. This is the reference to the square. And when that person asks you where on the Wenceslav Square, you can say under the tail. And this is some local local name that if both persons knows what does it mean, it's also explicit geodata. Or the second thing is that it may be done by the reference. So party at Jakub's place, if you know where Jakub lives, you know where it is. So that's it. This is the difference between implicit and explicit geodata. And both of them are in this manner considered geodata, which is quite important. So back where I have finished. So when we know that we are talking about the location, let's say about the implicit location, we know that we need to have some coordinate reference system, because we need some reference to which we are making the to which we are referencing the coordinates. So basically, most of you know World Geodetic System 1984, which is known as VGS84. Most of the internet maps you possibly know, like Mapit.cz or Google Maps, also maybe Big Maps, and I'm not sure how it's called, that maps from Apple, but also, this is also using the VGS84 system, as well as OpenStreetMap, which is open source database with Geodata. It's also running on the VGS84. And basically, coordinate reference system tells you which are the mathematical parameters of the coordinates we are using. How is it bound to the geoid? Because the Earth is not round, but it's geoidic. The geoid is a special shape of Earth, so it looks a little bit like a potato. And from that, you need a set of transformations, basically, how to get the location from that potato to flat. Usually flat. It doesn't have to be flat, but it has to be something which is referenceable by the mathematical rules. So usually we are using something which is called a reference ellipsoid. This is an ellipsoid which is trying to be bound to the surface of the geoid as much as possible in the place we are interested in. This is also quite important. The VGS84, the system most of you know, this is some universal system which is more or less precise for the whole Earth. More or less, I mean that it's in the let's say meters, small meters, okay, or maybe decimeters in some places. And it's quite okay if you are trying to get from Prague to Brno. You don't really care that the precision is only 2 meters. Yeah, but it may be a little bit more important if you are trying to set up the house or measure the distance between two atoms, for example. So we are using a lot of different coordinate reference systems, and their usage is basically that you have a very high precision in the region of your interest. So for example, in the Czech Republic, there is a coordinate reference system called Systém jednotné trigonometrické sítě katastrální, which is quite this is quite complicated system. Also in the worldwide, it's also quite a complicated system. But the thing is that this system is very precise in the area of the Czech Republic, Slovakian Republic, and part of the Ukraine. So because it was created in 1920. But it's really not really precise in any other place in the world. So for this, we need to have some reference ellipsoid, and then we are using a geodetical datum. Geodetical datum, it doesn't have anything to do with date. Datum is the way of transformation from the reference ellipsoid to some other reference object. And for those reference objects, we can have we need to get some projection from that object. Usually, we recognize three basic types of projection from some globe to flat. So we have the conical projection, planar projection, and cylindrical projection. And based on this, we have the coordinate reference system. Most of those systems, they are based on mathematical equations, and all of those equations are described on the page you can see here, EPSGIO. I will just open it that I can show you how it looks like. We can say GS84, and it will show us what it is. So, for example, this is it. So in here we can say how it looks like, or at least we see what is the geodetic reference system, what is the ellipsoid used, what is the geodetic datum.
Michal, you're still sharing the slide and not the browser.
I'm sorry. So this is something I need to. Okay, so I will stop sharing and I will be sharing the whole screen. Is it better now?
Yes.
Okay, so this is EPSGIO, and in here you can. Okay, I will go back. So from here you just can search by name. So VGS84 is valid input. I can choose from more systems. Basically, those three, they have the same geodetic system, the same ellipsoid, but they are using different projections. So basically, this one, VGS84 World Mercator, this is, or this one, Pseudo Mercator, this is the one which is used in most of the maps you know in the internet. So here in the picture, you can see how it looks like because it's transforming the data in always in any matter because we are transforming it from the geoid. And here you have the definition in the mathematical language. So this is the basic stuff about the coordinate reference system. I'm not giving you much information about that because this is quite complicated and there's a whole few subjects at our university. But I think that this is enough for you. I will tell you the three most used, or at least in our country. We have VGS84, which is the world geodetic system. Then we have ETRS 89, which is the European version of VGS84. This is a little bit more precise for the area of the whole Europe than VGS84, but the representation of the data and coordinates are the same. And then we have the systém jednotné trigonometrické sítě katastrální. This is the Czech one I was talking about a minute before. So there's plenty of systems, and this is what you need to know what you are doing. Okay, so what exactly is geodata? I was talking about implicit and explicit before. So I will move a little bit later. So we recognize vector representation of geodata or the raster representation of the geodata. Basically, most of the data nowadays are stored in some databases, geodatabases or regular databases with some geo extensions, or in the data itself. And most of that stuff is the vector representation. That means that I have some textual representation of data in the manner of coordinates. The raster representations, for example, if you take a paper map, this is perfect example of raster representation. You can also have the raster representation of data in the computer. Usually, nowadays, it works in a way that you generate some visualization of vector data, and you put it out as a raster. So it's a tile. Usually it's faster to serve by the services, and the basic stuff, basic difference is in vector representation we have the objects, and you can ask for the attributes of the whole objects. In raster representation, all you have is pixel, and in this way it's not as precise, but it's still useful for navigation. Usually you are okay with raster representation. And most of the things I will be talking about in the next hour will be regarded to the vector representation. In the vector representation of data, we recognize geometric objects. So if we are talking about geometry, we need to define what kind of object it is. So we have multiple categories: points, multi-points, lines, multi-lines, polygons, multi-polygons, or surfaces. Surfaces maybe also in 3D data. I will talk in detail about it a little bit later. And the thing is that it quite depends on the format you are using and on the platform you are using, but in some cases, you can create a geometry with curves. In some cases, you cannot. It's much simpler to do that without geometry, without the curves, sorry. But the difference is that if you want to create a circle, you would like to make it by 3 points or something like that, and you will create a circle. But this is quite difficult to process. So usually it is done that the circle is divided into a set of, let's say, 200 short lines, and it looks like a circle. It behaves almost like a circle, but it's just not a circle. So the representation of points. Usually we have, for every category, we have the points and multi-points, lines and polylines. So I will show you the difference. So the picture on the left, I have extracted from the mappy.cz, and I looked at the part of Southern Bohemia, and I wrote restaurant. So this is what I got back. This is the set of points, and every point represents a different restaurant. So every mark is a single point object. Point object is represented usually by the pair of coordinates. In the GeoJSON system, it will be latitude and longitude. In some other systems, it will be also latitude and longitude. For example, in the Czech system, jednotné trigonometrické sítě, it will not be latitude and longitude. This is something else, but it doesn't matter. On the picture on the right, you can see two types of points, or three types of points, sorry. First is bus stops, second is metro station or underground station, and the third is tram station. What do they have in common? All of them are a traffic station called Davidska. So this is the example of multi-point, let's say. If I look at all of the marks marking the underground station, so all of them are the entrances to that station. And of course, it depends on data. I could say that one entrance I can differ one entrance from another. But let's say that in this case, we are not doing that, and every entrance is an entrance to the same station. So all all of those points represents the underground station. Then we have lines. If we are representing the line, we can represent it as a line, which is on the left picture. This is the D1 D1 highway, or motorway from Prague to Brno. This is a straight line. On the right picture, we have the parking zones. The parking zones, usually the parking zones have some name or the code, and it aggregates more lines in one object. So in this case, on the right side, we have some purple zone close to the Prague main train station. So this is the multiline because it gathers multiple lines. And the same is for geometric objects. For the polygons, on the left picture, we can see the building in the area of Vinohrady Hospital. And this is the single polygon because it is one object that represents one geometry that represents one object. On the right side, we can see the multi-polygon. This is the area of the municipality of České Budějovice, and this has a specialty that you can see two polygons there, but both of them represents the area of the municipality, because the municipality is not in one piece. It's divided into two polygons. So these both polygons are representing one city. So one object is represented by multiple polygons. I hope you understand that. I forgot to say in the beginning that if you have any questions, if you do not understand anything during the presentation, just ask me, please. Okay. The next task is when we know how can we express the geometry, or what are the kinds of geometry objects? So we need to express it somehow in the data. And this is the first thing that most of the users, especially from the IT, not familiar with the geospatial sciences, so what are they doing? They just create something like a table with X and Y, let's say X and Y, or latitude, longitude columns, and they are putting the coordinates, single coordinates there. This is something which is done quite often, and this is not really good practice. We have some reasons why it is not a good practice. The first reason is that we want to represent the geometry as one attribute, not selected into X and Y coordinates. The second is that we need to specify what is the coordinate reference system used. It may be specified in the object itself, but it also may be specified as a standalone attribute or something like that. There are more ways how to do that. Another thing is that if we want to represent a point geometry, it could be okay like this, but if we want to represent a line or a polygon, you definitely need to have much more points from which the geometry object consists. So in this case, it would be really, really difficult to represent something more complex type of geometry. And even multi-polygons, this is also much more difficult. So this is not the good practice how to represent the data. So what is? We have, let's say, two standardized ways how to represent the geometry objects. And then we have much more, let's say, non-standardized ways how to represent those polygons, and those basic those objects, and they basically are based on the format we are using. Some of the formats are using these two standardized representations, and some of them not. But we will talk that later. So first geometry representation standard is well-known text, or WKT as it is shortened. This well-known text also has a binary way of writing. It's called well-known binary. but it's not really that helpful because random text is both human and machine readable in a way. And here in the first lines, you have two examples. So this is how to represent the point. Basically, point representation is that you have the name point, and in the brackets, you have the coordinates. The line string, which is basically the line, it's quite similar to this, that you have the name of the object and you have the set of the coordinates. The representation type, it's standardized. It's based on the OGC standard, and it's described both in the simple feature access standard, which is accessible from this URI, and also from ISO 19125. And in both of those standards, you have described how the random text works. If you want just to use it and not get lost in the scientific text, you could look in the Wikipedia. It's not so common that teachers are recommending you the Wikipedia pages, but in this case, this quite works, and you have shown it quite nice how to write the data. Yeah. If you remember that I was talking about the coordinate reference systems, the thing is that for WKT, usually most libraries which are working with that are expecting QGIS84. But basically the WKT supports various coordinate reference systems, but it's not like every library which is working with it can reach them. And basically in the standard, there is no strict rule how to represent the used coordinate reference systems. So the good practice is either create a standalone attribute for the coordinate reference system in the data, or the second is used in other standard, GeoSPARQL. We will be talking about it in the end of the presentation. And this is done that the name of the coordinate reference system in the form of IRI identifier is put in the beginning of the well-known text writing. And this is how it is used, in GeoSPARQL, and it is possible to use it almost anywhere else as well. It is not against the standard. And the second standard we have for geometry representation is geography markup language, which is basically something which is derived from XML. As you can see, this is XML way of writing, and it is really complex. It contains a lot of different geometry types. Not only those we were discussing before, but also the 3D objects. It supports various coordinate reference system. You can see how in this example that you have it as an attribute of the XML element. The coordinates are as nested elements, and it uses all the good stuff that are connected to the XML, but unfortunately it has all the disadvantages of the XML. First, it's really talky. Yeah, you need a lot of space to describe a simple object. But in the end, nowadays you have almost unlimited data storages, so I think it's not a big deal. Yeah. Okay. What else? Then we have format-based geometry representation types. And basically we have, let's say, 6-7 basic geometry formats for the spatial data, and some of them are using those standardized representation, and some of them are of course not. And they are using either something they have invented somehow, or some binary or database representation. So let's look at it. Okay, so let's get to the formats. Let's start with the spatial data logic. You may have mentioned, you may have noticed that we are talking basically about geometry. So we can tell that geometry is something like a special attribute or a special object in an object-oriented way of thinking. And this is basically the geometry is part of the data that represents those coordinates and coordinate reference systems and types of geometric objects. And basically in the data, we want to have anything else represented as usually. So the geometry is not the only attribute of the data. So in this example, I was trying to show that we have a house, and the house has some geometrical attributes. So basically this will be location and maybe shape. And the other attributes may be what is the connection to water, what is the type of heating in the house, how does it process the garbage, what kind of electricity it is connected to, what is the source of the energy, what is the boiling system in that house, and what are they cooking on, and this kind of stuff. So those are all of the other attributes. And the special attribute is the geometry. As I said, it may be expressed as attribute, or it may be expressed as a standalone object representing only the geometry. The important thing is that the object that may be spatially located is marked as a feature. Yeah, this is quite important word here. So feature is any object or any object model in the real world that may have any location. May have means that it doesn't necessarily have to has accessible geometry data. For example, if I have some information about, let's say, a forest, and some information about most of the trees in the forest. And for some of them, I may know the exact geometry, and for some of them, I do not. But I know that all those trees are part of that forest, and all of them are spatially localized. So then I can treat them as features, although I do not have the geometry. And based from this logic, all spatial data formats are based on. So let's go to the first format. We have already seen this name, geographic markup language. In the first case, it was the name of the geometry representation standard. In this case, it is a spatial format. So basically, this is an extension of XML. We can find a schema in this location, schemas OpenGIS.NET GML, and it specifies really complex. Note really complex set of geometry representation. Basically, we have those two types represented by those object types or classes. We have the abstract feature. Abstract feature is anything which can be spatially located, and it has some location, and the location is basically any kind of geometry. And based on this, we are modeling the data. I don't know if you are somehow fluent in XML or GML or XML data. So I will show you the real example of the data from the Inspire directive. So this is the XML element address, which contains attributes about some identifier, about some alternative identifier. Then we have the position, which is basically the geometry representation. And then we have some specification, and then it is composed from the components. This feature represents an address, and that address has a location where it is located, and then it has some components. In this case, the components are the functional parts of the address, like the street, municipality, house number, and this kind of stuff. And you cannot see any feature, or you can see geometry here, but you cannot see the word feature here. This is because we have an XSD schema, and the XSD schema for this XML structure defines that every address is subclass of feature or abstract feature, and this position is, or this AD geometry is subclass of abstract geometry or abstract location. So those two classes are filled in this way. It is used quite a lot. This is one of the most complex way how to represent the spatial data. It is basically used by the infrastructure for spatial information in Europe, which is a directive of European Commission from 2008, and its goal is to share or standardized spatial data about environment across Europe in the standardized way. So in the first case, all of the data, or 99% of the data published in accomplishing this directive is published in this GML format. So you can find quite a lot of data in this format. And the catalog of this European directive you can find here in NPRG036-l10 EC Europe EU. Maybe I can click on it so you can see that there's really quite a lot of data. So we can search it by the country. So let's say, look how many data we have in the Czech Republic. Yeah, so you have 164 entries, and most of them will be in the GML. Here you can see those addresses I was showing you in the example. And basically, yes, all of those data are available in GML. Okay, the next format we are talking about is GeoJSON. As geography markup language was extension of XML formats, GeoJSON is extension of the JSON formats. JSON has some advantages from XML and some disadvantages, and in the GeoJSON it works as well. So GeoJSON, it's usually much faster. It takes much less space. It's maybe a little bit easier to see what the data means. And the bad stuff about the GeoJSON, if we are comparing it just in the GeoJSON versus GML way, the GeoJSON does not support any other coordinate reference systems than GS84. In the example here, you can see that we have some CRS here defined, but this is not the standardized way. This is not written in the standard. In the standard, you have only this, right? Geometry has coordinates, and those coordinates are 14 dot something, 50 dot something. The coordinate reference system here is the standalone attribute. In the earlier versions of GeoJSON, there was support for other coordinate reference systems, but it was removed because it brought more complications than what was the advantage. And the thing is that GeoJSON is usually used as the exchange format on the internet. to show the data in the maps. And like 99% of the data you want to publish in the internet are in the VGS84, sorry, in the VGS84 coordinate reference system anyway. So this was removed. The basic rules on how GeoJSON data should look like are just two compared to any other JSON. The first is that you have the geometry attribute there. The geometry attribute has two sub-attributes, coordinates, which contain the coordinates in this way, like divided with commas. It is quite similar to WKT, the well-known text, but it's not the same. So take care about it if you want to use it. Look at the standard, and the second attribute is type. The supported types are listed: point, multipoint, line string, multiline string, polygon, and multi-polygon. So all of them are represented. It can represent, or it is suitable mainly for 2D for the representations of 2D objects. And okay, the second attribute, which is let's say required, but it's not written directly in the standard, is that the whole object shall have type feature. Yeah, and the thing is, it's not written in the standard directly that it has to be in this way. But if you would like to open the GeoJSON in any software in a Mac, and you don't have it there, the type feature, then it will not work. It's as easy as this. There are two interesting stuff in a practical way for GeoJSON. The first is that if you want to create a GeoJSON file, it's really easy. You can look at the web page http geojson.io. I will cancel the last time I did it. So, and in here you can see that on the left side you have the representation of the map, and on the right side you have something which looks like some text editor. And you can get anywhere in the map. So let's get to Prague, for example, to the Leicester Town Square. Yes. Okay, we're here, and I can here select the point and click here to the entrance to the mathematical physical faculty, and now I have the generated GeoJSON representation of that point, yeah, in here. And if I say that I want to have the polygon as well, I can draw a building. Let's say like this. It can be quite simple. And now I have the polygon representation of the GeoJSON. So this is a really easy way how to create the GeoJSON data. And from here, I can create. I can add any other attributes here, but basically this is what it is. That I have the feature, and it has some geometry, and all other properties can be here or as a standard property somewhere else. This is quite okay. And from here, I can save those data. I can click save here, and I can save it as the GeoJSON, and I can also save it in other formats or other representations. So, for example, I can save it as well-known text here. So if I click this, and I will click open in text editor, you can see that I have those two geometry objects represented in well-known text. So this is quite powerful tool. If I download it as a GeoJSON, I will use this, I will save it, and I will use it to show you another good thing about GeoJSON. I believe that all of you are using GitHub to do stuff, and I will show you one of my okay, I have some yeah, so open repository here. So I will upload the file I have just downloaded to GitHub repository. Download small GeoJSON. Okay, so it doesn't look this way, so I need to just the file, upload file, downloads, not GeoJSON. I will commit it directly. Okay, and now when I open the map GeoJSON in GitHub, it's directly visualized in a map. So this is the easiest way how to create a web map in GitHub from the GeoJSON, of course. So let's go back to the presentation. So this is the GeoJSON or GeoJSON. This is quite powerful, but it has its flaws. It's really helpful if all you want to do is just publish your data in the internet, show it in some online map. It's working quite fast, and it has a wide support in the existing libraries. But count on that you can represent only 2D geometries, and you cannot have the data in any other coordinate reference system that WGS84. Then we move to the Shapefile. This is quite a popular format. This format was created by the Esri company. Esri company is the manufacturer of the most used GIS software in the world, and it was founded in the early 80s. The Shapefile format was found in late 80s, let's say. The current version is from the late 80s, yes, and it's visible there. So it has a lot of restrictions. And I think that if you are the new users of the if you are new to the spatial data, I would recommend you basically anything else than Shapefile. The thing is that Shapefile, it consists from 5 to 8 single files. So it's not a single file. You need to have 4 to 7 more files in the directory to represent your data. The name of the attributes are limited to 8 characters, which is also quite nonsense in this time. Another thing is that in every data set you can have objects of only one type. Basically, if you have let's say buildings, so you may have only buildings in one data set. You cannot have any other object types in that data set, which may sound pity and that it's not really useful at all. But on the other hand, you are using quite from that in one data set you have more files, and all other formats I was talking about before supports that. Of course, I can express more types of geometry and more types of objects in one file in GML and both in GeoJSON. The thing is that this is, of course, native format in one of the most used commercial software. So basically, 90% of administration all around the world is using shapefiles, unfortunately. Next format is OGC GeoPackage. I'm not showing any sample data here because OGC GeoPackage is basically SQL-like database, and it works quite fine. In fact, when I'm doing something with the spatial data nowadays, in 9 times out of 10 cases, I'm using GeoPackage right now because it is the fastest and most lightweight way how to store the geodata now. And in one file, you may have several object types, several feature types, several kinds of geometries, and you can also combine vector and raster data in one file. Which is quite good. The disadvantage is that you do not see the data uh, until you open it in format in some software which can read the format. So basically, some GI software, and this is basically the only disadvantage I see here. Uh, I remember that like 4 years ago we were testing it. One of my friends asked me how to store a lot of data because he was using shapefiles, and it took him like 6 hours to upload the data in the uh, web software. And I recommended him the OGC GeoPackage, and what took him 6 hours, wait, no, it was 2 hours, sorry, 2 hours with Shapefile, he had in 5 minutes with GeoPackage. So it is really, really fast and very complex. And some people are using comma separated values, so it is the easiest way how to store geodata somewhere, because CSV files are used in any other data science. So it is also it is of course used also in the geospatial data science. It is very easy, and it is let's say MS Excel friendly. Those are two biggest advantages. Also, it does not have any recommended geometry representation type, which may be positive because you can use anything you want. So I think that the best way how to represent. So if you want to use comma separated values, I would recommend you to use the well-known text geometry, and then it's not as bad, and it may be quite useful. And the bad thing is that the geometry representation in well-known text contains commas, and the comma separated values also contain commas. So you need to take care that the data are valid. So we need to take care about escaping the commas. So you can usually pack it all in the quotes, and it's okay. But if you are using some more complex geometry representation, you can also have the quotes in the geometry representation. So you really need to take care about the escaping of the special characters here. So now I will talk about spatial linked data formats. So this is a special category because it behaves in a little bit different way. Usually, if you just want to publish the data in some format which is good for analysis, you are using the regular formats. Spatial linked data formats are used if you want to have the data linked in some wider contexts, and usually we are talking about RDF here. I heard that you also have some bases in the RDF, which is perfect. So I will start directly with 3 types of representation of geodata in the linked way. So first, this is the most simple way how to represent geometry in RDF. So it's called GeoVGS84, and this is the namespace in which the ontology exists. And basically, we have the representation of the point object, which has 2 attributes, latitude and longitude, and that's it. The advantage is that it works perfectly fine if all you need to represent is points in VGS84. And disadvantages are that it cannot represent anything else. And also I have the comment here that it uses let and long, and from this it is visible that the creator had no big knowledge, or what I don't say knowledge, but the basis in the geospatial sciences, because in geospatial sciences we are not using the long, but only three letters: long, lat, and long. Okay, second way, more complex. I would say the most complex way how to represent the data is in linked spatial data is GeoSPARQL. It consists of the ontology and the query language system, and the query language supports the spatial operations, and it can also be used for express the data itself, of course. And in here we have two types of object, which is feature. Feature represents everything. Feature represents the object from the real world, and it contains all the attributes. And then it contains a relator has geometry, which references to the geometry object. And the geometry object has nothing else to do than represent the geometry either as well-known text or as a GML representation. Those representations are represented as literals. So basically those are strings, let's say. And using this type of geometry representation, GML representation, you are able to represent any object, any spatial object you can. So it supports 3D geometries, it supports various coordinate reference systems, it supports everything, and it also supports some spatial operations. We will finish this presentation with the spatial operations. The bad stuff is that it may be too complicated for beginners, and it may also seem overpowered. So for simpler representations of some stuff, for example, points. We were discussing it like 2 weeks ago with my coworkers that one of my coworkers, he needs just to represent the geometry. Yeah, the geometry of his features is just points, and it's in VGS84. And he was doing everything he could to avoid GeoSPARQL. Because it seems too overpowered or too difficult for him to use. But in the end, if you learn this, I think it's the easiest way or the most complex way how to do it. And this is the example of the data, how it looks like. So this is the real world example we were doing like 5 years ago. Yeah, 2018. So 4 years ago, 3 years ago. Yeah, 2 years ago, we were doing this for IPR, Institute for Planning and Development of Prague. And we were basically transforming their open data into linked data, version. I'm not sure it is published somewhere on their pages. I think maybe not, but we have the pipelines to recreate it. So we are working with them on further projects. So I think it will be published maybe someday. And you can see here that you have the object. This is the object, and its type is GeoSPARQL feature. It has a special attribute. GeoSPARQL has geometry, and this has geometry is referencing to the geometry object. And this geometry object has a well-known text representation, which is described here. So that's it. And last format I want to show you is GeoJSON LD. I believe that you have heard about JSON LD. It's basically about adding the context to the JSON data. So this is the extension that you are adding the context to the GeoJSON data. So on the left side, you have some sample data of the GeoJSON LD. This is the sample of the data. So we have some type, which is location. The name is name of the object is nothing but Shumava, and its geometry is point with those coordinates. And we have the link to the context, and the context is mapping the attributes to some RDF model. It's shortened, of course, because this was quite long, and this is that the Lowsian geometry is contextually mapped to this GeoJSON context JSON LD. So basically that's it. This example, this is a real life example from the open formal norms pages from the Ministry of Interior. This is the project I'm co-working with Jakub Klimek and a lot of other people. Some of them are also from the MATFACE. So this is something which really exists. And this was basically everything to the formats itself. And the last chapter I have here is how much time I have? Like, yeah, 20 minutes. It's okay. So last chapter is about spatial relations and spatial operations. So this is basically what can we do with the data, with the spatial data, what are the spatial types of analysis and operations we can use only for the spatial data because we need a location. And at this point, I would like to ask you if you have any questions to the formats. Okay, it doesn't look like someone has any questions. So in that case, I will continue with the stuff and we can leave the questions for the very end of the presentation if there will be any. So let's talk first about the spatial relations. So spatial relations, it's special kind of relation between two or more objects, and it's usually based on the location or shape. So that's quite logical. In the IT, it's usually presented as any function which returns true or false. And it returns true in the case when the relation is fulfilled, the condition is fulfilled, and false if it's not fulfilled. So we have four, sometimes it's called 5 basic types of spatial relations. The first relation is topological, and we recognize 8 basic topological relation types. So I have listed only 6 because the other 2 are able to get from these 6. So basically, we have the operation or the relation within, which means that object A is fully within the object B. So basically, this relation is fulfilled in the case when no points from the object A are outside of the scope of object B. This is basically used in the case that you have, let's say, a building, and the building is represented by the polygon, and then you have representation of the entrances to that building, and those entrances are represented as points. And when you have the data, it is best practice to do the topological validation of the data, which means that the data do not have any errors, which will cause trouble in the future. And out of the most common topological error is that those points are not within the polygon. So in this case, you are just testing that all of those entrances are inside the polygon of the building, because entrance cannot be outside of the building, of course. Second topological relation is touches. Touches is used only between two polygons, or between polygon and a line. You could maybe have it between two polylines or multi-lines as well. But the thing is that two polygons or two objects touches in the case that only the border lines or the points on the border of the object are the same as the border points from the border of another object. So those two polygons are touching. If you look at the picture in the lower right corner with the overlaps, uh, those are not touching because they share not only the border points but also some points which are inside of the polygons. So this is the difference. The basically third relation is crosses. Crosses is also between two lines or line and a polygon, and between two lines it means that those two lines have exactly one shared point. Between the line and the polygon, it means that the line is going through the polygon. That means that some of the points are shared with the polygon and some are not. This is the crosses. And last spatial relation I will talk about here is the overlaps. So overlaps is relation between two polygons, and that means that some of the points of the both polygons are shared, and it's not only the border polygons. We have two more spatial relations which are derivable from those ones. One of them is contains, and contains is basically reversed within. So within means that the polygon A is in the polygon B. Contains would mean that polygon B contains the polygon A. And the last one I do not remember right now, but I think that if you are interested, you can Google that anyway. Second type of spatial relation is directional relation. In the vector data, you may have oriented edges, and it's quite common stuff in the spatial data. And basically, this means that you have the line which is oriented, and let's say this is the road, like the one direction, one-way road. And we can say this man is standing left from the road, and this woman is standing right from the road. So this is the spatial relation between the position of those two people and the road. Third type of the spatial relation is the distance relation, which basically means how far how far are the objects from each other. Yeah, so for example, we can see now that the distance between the man and the house is 1.8 kilometers. The distance between the woman and the house is 2.6 kilometers. And from this, using the spatial analysis, we can analyze that the man is standing closer to the home than his wife. So that's it. And of course, in some literature, the temporal aspect of objects are also in a way spatial aspects of the objects, and it means that we can compare the location in time. So, for example, in here we can see that in 1 hour, the man have moved from a place he was staying before, so he moved somewhere else. His distance has changed. His wife also moved in some way. Her distance also changed, and we can do some analysis and some processing based on those relations. So this is quite this can be quite complicated. This is just opening. How does it look like? What can we do with the temporal spatial relations? I will drink a little bit of water, so give me 12 seconds, please. Fine. So let's get to the next slide. Yeah, I will tell you something about operations and basically spatial operations. This is something what I can some way of the analysis of the data. I can use it to do some research, find some new relations. Based on the analysis, I can do a lot of stuff. So one of the basic operation is buffer. Buffer basically means that I will extend the area from the object by the specific distance. So if we have the basic string here and we set up a distance, the buffer operation creates a polygon in which all points are at most at the distance of a predefined distance from the all of the points of the origin object. So basically, from a point, the buffer is a circle. And for the line, it's some kind of polygon. For the multipoint, it looks like this. And when we are using a polygon which may have a hole in it, which is okay, the buffer also may have a hole, but if the distance is far enough, the hole will disappear. What is it used for? Basically, when you are, for example, if you are standing in a place and you are looking for the closest restaurant from your place, you are usually doing buffer. Then we have union, difference, and intersection. Basically, this is the spatial operation. On the output, you have two spatial objects, and in the case of union, on the output, you have one object which contains all of the points that were in both of the objects on the input. For the difference on the output are only those points that were not shared. And in the intersection, on the other hand, in the output, we have only the polygon made only from the points which are shared by both of the input objects. This is used quite often. This is similar. If you know if you are using Photoshop or GIMP or some other softwares for working with graphics, you basically know that in the selection tools you have something which is doing this kind of operations: the union, difference, intersection. And in the spatial data analysis, you are using it for the similar use cases. Then we have clip. Basically, in clip, you have two objects in the input. First object is what is the basis, and the second is what is it? How the object for which it is clipped. And on the output, you have all points from the first object which are not shared with the second object. Then we have spatial operations. This spatial operation distance. This operation basically returns you the closest distance between two objects. Just know that if you have polygons, you will get the closest distance. So from the closest edges of both of the polygons. And the last spatial operation I will show here is convex hull. This operation is also used quite a lot. I will tell you where. And this operation takes an object, basically a polygon, and on the output it returns a convex hull, which means that there will be only convex angles in the output object. So from the 5-point star, you will get the pentagon, and similar is convex is a bounding box. Basically, bounding box returns the minimal rectangular area, which is of the object, which is also oriented from north to the south and from east to the west. And this is usually used, for example, for the centering of the map in the web maps, or it may be used, for example, if you want to have some indexing in spatial databases. You need usually classical indexes like in normal databases that will help you finding on the other attributes. But when you want to simplify the searching or querying the data based on the geometry, you will store the data as the convex hulls, and the spatial operations, other spatial operations, and processing of the spatial relations is then much faster. So those are the reasons why this used. And in last, I don't know how much time I have left, like 9 minutes. So in last 3 minutes or something like that, I will tell you what is the GI software and what are the spatial libraries that are used the most. So basically in the GI software, I would recommend you for the normal usage, the QGIS. You can download it from this website, and this is open source project, which is very powerful. It supports all of the geodata format I have shown you in this presentation, except the linked data formats. And it supports all of the spatial operations and spatial relations that I have shown you. Then we have PostGIS, which is basically the spatial extension for PostgreSQL database system. And this is useful for doing some operations on the database level. And it is also quite powerful. And then I could mention S-JTSK, which is commercial software from the beginning of the 80s. It's basically one of the oldest GIS softwares, together with GrassGIS. I haven't mentioned GrassGIS here, but it's also very powerful. ArcGIS, it's commercial software, so you need to buy it to use it, and they are trying to use to force you to using their data formats, which have some disadvantages, of course, but you are really able to use all other stuff there as well. Everything I have showed you here is possible to do in S3 ArcGIS. And I think that maybe some of the operations and some of the spatial relations are there very nicely processed. So it's it definitely is good, but you need to have money for that, and it's not really easy to add some extension for that. For QGIS, it's much easier. Okay, and for using the spatial data on the internet or just some simple visualization of the data, you can use some spatial libraries, basically Leaflet and OpenLayers. I would go for those two. Both are JavaScript based APIs. Basically, Leaflet has also a React component, so you can include it in your Java project or React project. And then we have some projects like Map Server or GeoServer. Those are the heavy solutions, and they contain from most of the stuff I have mentioned in the beginning of the presentation that are part of the geosciences. So they allow you to store the data, transform it in any way, do the analysis there, publish the data to the public, and a lot of other stuff. Those two, map server and GeoServer, they are both open source. So this is also quite interesting tool to look for. And that's all from my side. So I hope that it was not too abstract for me. I tried to show you most of the data in some practical way. So I hope I succeeded at least a little bit.
Thank you. And are there any questions for Michal? Okay, so if not, I expect everything from today's lecture is clear. I think it was very informative, and thank you again, Michal.
You're welcome.